Okay, good to go. Apologies for that. We're good to go live.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, and welcome all to this workshop on Earth observation foundation models with Prithvi-EO 2.0 and TerraTorch. My name is Andrea Manara from the ITU, the International Telecommunication Union, and it is a real pleasure for me to introduce a new episode in the GeoAI Discovery series. We launched this series beginning of 2022, and we discussed the GeoAI application policies, ethics, the future of GeoAI for good. Thematic session included climate actions, spatial digital twins, energy ecology, agriculture, water and food system, health, and many more. Current focus of the series is on geospatial large language models, and in the organization of a hands-on workshop focused on building up practical skills in applying AI to geospatial data under the leadership of the curator of this series, Maria Brovelli. If you missed some episodes, don't worry, you can watch the recordings of those events on YouTube or in the neural network to which you are connected right now. Without further ado, let me now introduce Maria Brovelli, who will moderate these events. Hello, Maria. So, Maria is professor of GIS at the Politecnico di Milano at the Geoinformatics Engineering course of study, member of the Schools of Doctoral Studies in Data Science and Earth Observation at Roma La Sapienza. Amongst her many activities, Maria is Vice President of the Commission of Geospatial Information of ISPRS, member of the Board of UN Global Geospatial Information Management Academic Network, and co-chair of the United Nations Open GIS Initiative. Welcome, Maria, and the floor is yours.
Thank you, Andrea, as usual, for your nice presentation. And welcome to everyone. Good day, good morning, good evening, good afternoon, depending where you are. We have a lot of people connected because the topic of today is absolutely interesting, and so attracting a lot of people. As Andrea said, today we are dealing with this powerful tool, which is Prithvi-EO 2.0 foundation model, which is developed by NASA and IBM. And the presenter of today will explain us how This tool can be used with TerraTorch to perform flexible geospatial tasks. Specifically, we will see some use cases and the image classification. So we learn how to classify satellite imagery for land cover mapping, segmentation, and also doing regression. But without stealing time, I want to introduce the speaker of today. We are very glad of having here a young and very talented researcher. So Paolo Fraccaro, welcome. Paolo is a certified distinguished data scientist at IBM Research Europe, and he has an extensive research experience in data science and AI applied to solve a huge range of scientific and business problems. Paolo contributed to the development and commercialization of key research technologies and solutions, feeding into platforms like the IBM Environmental Intelligence Suite and the Geospatial Studios, among others. And then Paolo is leading a global team focused on the development and benchmarking of Earth observation foundation models for IBM research, collaborating with key partners like NASA, ESA, and the AI Alliance. So thank you, Paolo, for being here, and thank you also for accepting of doing this hands-on for all the people who are interested. So very welcome, and I give you the floor now.
Thanks, Maria, for the kind words and introduction. I hope not to disappoint Maria and others. We'll have 3 different use cases. We opted for not having classification, although I'll show that there are examples that can be found in TerraTorch, just because it's a little bit easier than the others, and we want to do and show some progression in the more relevant task of segmentation and regression. So this was just a premise for you, Marie. Otherwise, yeah, I'm Paolo Fraccaro, and I'll be leading the session today. I'll share my screen now. I have a few slides just to set the scene on what we have done with Prithvi-2, and also what are the differences, for example, to Prithvi-1, as well as a premise on bringing everybody on the same page around the foundation models. So I'm leading the session, but because it's not a presentation, a hands-on session, we have 3 of my colleagues, Benedict, Romeo, and Blair, who will be helping out if there are any issues. You should have received 2 links. If not, maybe Julian, if you can share. One link is for the Slack for the TerraTorch. You don't know maybe what TerraTorch is yet, but I'll tell you. And this is for the hands-on. And then the other link is where to find the examples that we'll run on today. In case you didn't get access, there was limited access to the Red Hat platform that I'm going to run things today on. And maybe you want to run it on your laptop or something like that. Okay, so I'll assume that the questions and problems and so on are kind of handled by my colleagues, but please, guys, stop me if there is anything that needs taken care of during the presentation or the hands-on. So I'll start just giving this chart around the evolution of ML kind of AI algorithms over the last few years. So we started with expert systems where we had manually crafted rules most of the time. If then you see it on the picture. Then in the 80s up to the 2010s, we had this data that kept increasing in terms of label data, and we started having more consistent use of machine learning and classical machine learning. So we're looking at decision trees, subgroup vector machine, artificial neural network that are for sure older than deep learning. We're already there. Then we moved on adding, we had big data. We added also the computation that allowed us then to move to deep learning, which, however, required a massive amount of labeled data. And finally, we got to this latest stage of the last few years that probably we already moved on with agents, but to foundation models where we have massive unlabeled data, and we have massive computation, and then we use these self-supervised techniques to pre-train these models and then specialize them in specific tasks that we are interested in. And this goes beyond EO, right? This is a more general statement. I just wanted to show this one for maybe people that are not familiar with the flow. This is what basically we followed for Prithvi, but for mass autoencoders, mass image modeling is something that would be applicable for many other models, and for models that are trained differently, then we would have a different self-supervised technique that is used here. So we need to sample data at scale to preserve and obtain a diversity in a data set that we are going to use, a labeled data set that we're going to use to pre-train our model. Once we have done that and we were happy that we're covering the areas, the aspects that we want our model to be useful for, then there is always some data quality, clouds, not clouds, depending on which sensor you're using. Different parts of the Earth have a specific reflection. For example, if you look at optical data, then there is the technique that we use for self-supervised learning. We use mass image modeling for Prithvi. There are more contrastive loss focused techniques and so on. What we want to obtain is basically an encoder that because of these self-supervised learning that has done, is able to extract very relevant features from the data that we are targeting. In this case, with Prithvi, we were targeting HLS, but we can see later that the model goes beyond. And then we can reuse with a much smaller task-specific labeled data set for supervised learning. And then this is just closing the cycle. We close the cycle, so we have the task-specific labeled data. We combine an encoder with the task-specific decoder. We train it, and then we can use it for inference. Where, to use an analogy with text, the prompt in our case is really the geolocation and time where we want to run our model. Concerning Prithvi-2, has some key innovations to Prithvi-1, has been trained on a much bigger data set that is about 20-fold, if I'm not mistaken, so about 4.2 million global samples. We went for a bigger model, and it seems to have paid off. There is a possibility to bring in temporal and location information as well. And the thing that in Prithvi-1 we did was to validate against this environmental task that especially NASA was interested in. For V2, we did that, but also we added some community recognized standard around geobench for the validation. And throughout the project also we had SMEs from the NASA Impact Network that were involved to steer a little bit, help us understanding how to make sure that the model would be very relevant for the community. Just a brief overview of what GeoBench is. GeoBench is basically a set of data sets, is a 6 classification and 6 segmentation data sets that cover some environmental tasks, but also some more computer vision-like tasks, for example, identifying solar panels on roofs or tracking cattle in a field and so on. So you can see that Prithvi was trained at 30-meter res, and we tested it also beyond. If you see my mouse, this cattle one is actually beyond 1 meter as some other data sets in GeoBench. I'm not going through the detail here, just to show that what we were really happy to see is that this is the overall performance by averaging the performance of Prithvi across all the different runs, across all the different data sets. So we have Prithvi-1 here, and with the same exact architecture, but more data, we could get an improvement. So this was really good to see that all the work that we have done on the data prep really paid off. Then we have the 300 million version that is kind of par with other similarly sized, for example, DOFA data sets, models. And then it was really nice to see that the temporal location version is better than the non-temporal location version. And finally, the bigger model is the one that is performing the best. So here we have compared against 6 other foundation models and Prithvi-EO-1. This is the other side of what we're going to see today. Basically is how to use TerraTorch, which is this geospatial toolkit to fine-tune foundation models, geospatial foundation models for some key applications. This is has been initiated by IBM. But we have a growing community of developers, and we really encourage the community to get involved, submit issues. If there are PRs about things that people want to see and want to develop, that would be fantastic. And Prithvi is there, but for example, other mainstream models are there as well, like Clay, DOFA, Satlas, and others. For now, we have classification, segmentation, pixel-wise regression task, and we hope we're really, really close to have also object detection to add in the next few weeks. And you'll see that you can basically use it through a notebook, but also through some config files. So I think this was the last slide that I had. I'll stop sharing this one and just check that. Yeah, I'm not seeing any message, so I'll then share my my browser instead. Which I hope you can see. Can people confirm that they can see my browser?
Yeah.
Perfect.
Yes. Yes.
Yeah, fantastic. So just on the back of what I was talking about before, we have this Hugging Face page with NASA, where you can find all the related to Prithvi-EO 2.0. There is still stuff on Prithvi-EO 1.0, and also this weather and climate model that will be the focus of next session. We have a technical report. You can find all these links from here. Technical report if you want to know more. And also there is a dedicated repo with the configs that we used and some more details as well. I was saying that there should be this other link with these examples that people that have access to the Red Hat OpenShift AI will have there. If people want to do that on their own, then this is exactly the same. And for the data sets and models I'm going to pick, then there is a Google Drive that should download. For the amount that we didn't expect to have, there might be some glitch around the Google Drive API to get stuff, but you can do it also another time in your own time. Okay, so I'll go through things. I hope everybody has, unless there are any questions that I should be replying to or show something, guys, maybe if you can let me know on the IBM side if I'm good to go or not, if there are questions, because I don't seem to see any question. Okay, I'll assume that everything is fine. So this is Red Hat OpenShift AI, and that's the environment that I'm going to run the session on today. And people should have access to this. So if we go in the home, you see there are different data science projects. There are different data science projects, one per person that signed up with their GitHub handle. And therefore, if I want to go to mine, I would go to data science projects, and then I would put the handle that I provided. It might be cut off, but it's okay. And then I would click on it, workbenches, and then I have mine running. So I repeat so people can see it again. I would go on home, data science projects, and then here I type my name. I click on it, workbenches, and I have mine running. If it's basically not running, there should be start here, and usually takes a minute or so, maybe a little bit longer the very first time. But otherwise, then you can just click start running, and then you click on this, and you'll access an environment like this. So we should be automatically set up on this working directory. If not, then you should have this TerraTorch folder that we're not going to use. But there is this workshop one that we are going to use. And in here, we have two things. We have the data sets and the checkpoints of a little bit more trained models that we're going to use to see some insights from these data sets, and the three use cases that we're going to go through. One is about burn scars. Another one is about the multi-temporal crop segmentation, and these two are segmentation. Instead, this AGB one above ground biomass one is a regression. So I'll start with the burn scar one. So we kind of go in order of, let's say, difficulty for the model to learn. First easier, and then after more complex things. And hopefully this will be clear when I go through it. So we should have all the requirements already installed for us. So all good, and this was part of this setup. So should be all taken care of. We import our dependencies or libraries that we're going to use. And for the people that might try this on Colab, there is this change of runtime. All the people that are using Red Hat OpenShift AI should have a dedicated GPU for this event. So the first thing that we do is to run this cell because we already have this file. It's not going to download it. If you run it somewhere where this is not available, then you'll have that done. We are unpacking the data. So this is the data set. It takes a minute or so. Can people let me know if all is good? There is no issues so far. That would be helpful. Why it does that? All good. Okay. And this is the one that actually takes a little bit longer because the data is a little bit bigger. But there you go. We are finished. So the data that we have unpacked our folder, and what we have here is basically just some TIFF files. We'll see how they look like. You see that there is this pattern where the images, the satellite imagery, the HLS satellite imagery is already given away that this is 512 by 512 patches, have this underscore merged syntax, and instead the labels for burn scars is they have this mask suffix. So the first thing, so if we think about training a model, we have basically three main things. One is the data part, and this is what we are taking care of in this cell. So we are setting up a data module. And this is one of the characteristics or peculiarities of TerraTorch. We try to make it easier for people just to get started, and we try to take care of things as much as we can, giving them expert users the ability then to customize things as they want. Reason why I say that is that conversely to other libraries, so we came up with this generic non-geo, and this non-geo is just a loaded way to say that we are basically dealing with the images. We're not dealing with, for example, big tiles that come directly from ESA or NASA and so on. And we have these generic data modules. You'll see there is one for segmentation, there is one for classification that we're not going to see, but I'll show where people can find the examples, or maybe my colleagues can just post the link to where all the TerraTorch examples are. There is a regression one as well. So usually you have to create a new data set, you have to take care of a few things and so on. What we did was basically to assume that the data is provided either in the same folder or in different folders. So here you see that the data is actually in the same folder. So you have all this data in the same folder. But we can pick what is train, what is val, what is test based on a list. So if we go here, the data is all here, and I won't click here because there are a lot of files and it might complain about loading them. But you see, we have validation and we have train. So these are all the different the different files that we have in our data set. And how do we match images against labels? Well, we basically have that prefix that was in these files, and then we can identify what is an image for the model to learn from, and a label based on this suffix that I was telling you about. Then we can provide different transforms. This is an argumentation one that has together a random flips orientation. This is conversion to tensor. And in this case, we don't do any, it's not necessary any transformation for validation and test set. and then the means and the standard deviation for the normalization. And this is fairly important because I even lost a day. So if people didn't receive the Red Hat link, sorry, I'm looking at the chat. Maybe Blair and Romeo, if you can look at that, it would be good. So I'll carry on. Let me know.
Paolo, don't worry. If there are questions in the chat, I will let you know. So
Okay.
don't worry.
Cool. Yeah, that's okay. So this is fairly important because, for example, if there are some no data and either you're aware or you're not aware, without this is going to basically calculate losses with nonce. And I spent basically a day last week not seeing that this wasn't there, and I wasn't figuring out what was wrong. So this is very important. But long story short, you see that we can use our data that is in TIFF format by just telling this data module where it is, where the data is, providing some splits. We'll see that in some other use cases, we don't even need the split files. Normalization, and we're good to go. So basically, this is you know, a difference already to what other libraries can offer. Okay, so we spoke about the data. How does it look like? So we have our HLS images, 512 by 512, and this is a burnt scar in red and background in blue. So you can see that there is some signature. Sometimes is more apparent than other times, but this would be maybe of the use cases we look at today the easiest, I would say, and we'll see also this from the results that we got. The other thing that we need as far as the modeling is two other things. So we need the model, and we need also the way we are going to train the model. So I'm going to, and maybe you guys can do the same, I'm going to just kick off these next to basically cells, and then while these trains, because it takes about 4 or 5 minutes, we can go through this cell. So we said the data, we took care of the data with a data module, the model itself. And this is where there is another differentiation with TerraTorch compared to other libraries. So for example, TorchGeo has, and we heavily inspired initially from it, a segmentation task, semantic segmentation task. However, the key characteristic of TerraTorch is that we want people to be able to mix and match encoders and decoders for their own applications. So we want to make it flexible, and we want to have, and this is also you know, a call for the community, people that are on the call, have as many foundation models as possible. As I said, you can submit a PR with your model, and we can add it, and combine those with the decoders that I was telling you before for task-specific applications. So the way that we define a model in our case is through these factories. This is the more flexible one. It's called encoder-decoder factory. And it should be self-explanatory because we combine a backbone or an encoder with a decoder for a specific task. So going through this one, obviously the session is about Prithvi. There are different options to use Prithvi, and the only thing that you have to do is really select one of these, right? There is the 300 without the TNL, the time and location embeddings, but it's just underscore TNL to add it. If you select pre-train through, is going to pull the data or the checkpoint directly from Hugging Face. We'll see this one in a second in the other use case. In this case, we just have one time frame. Prithvi can digest different number of time frames, but in this case, it's just one. We're looking at one image and we want to identify the bird scar. Backbone image, the bands that are data that is coming from the data module referred to, and this is just because it's flexible to mapping the pre-trained weights of the patch embedding, the first layer, to the data that is actually coming. So imagine that maybe it was in different order, or it was a subset. I'll show you in the printout. It should be there what I mean in a second, but we handle that automatically. Then to do this segmentation task, we have at this point, imagine the features are coming out from our backbone, and we need some spatial operations or learned operations that will allow us to use different decoders. In this case, I'm using a UNet decoder, which is the one of the very famous ResNet UNet architecture. But that is a hierarchical decoder. So it expects the features coming out from the model in a particular way, a hierarchical way. And coming out from a transformer, the features are not hierarchical, might be hierarchically semantically, but not in the embedding dimension. So the first thing that we do, because the decoder expects 4 sets of embeddings at different stages of the transformer, is adding a neck which is called select indices, and we basically have the extraction of these features at some particular places that for the 300 are these, and for the 100 are these. So you can see how the bigger the model, the more deep it is. Then the other thing that we do, we go from tokens to image-like tokens. And then we do this learned interpolated to pyramidal. That is basically once we have the features in an image-like, but not a hierarchical fashion, it basically transforms the features in a way that the decoder is expecting. This is a classic number of embedding dimension for the UNet, and then there are some other things for the number of classes and some regularization. The other thing that we need for training that is the trainer itself, right? And sorry, last thing also, as part of the task also, we define, for example, the loss, which optimizer, and some more metadata about the data set itself. So 0 is no burned and 1 is burned. Then we have the trainer. This is not from TerraTorch. This is a plain PyTorch Lightning trainer. And we are basically using some defaults around the accelerator, the strategy. So here would be where you start bringing in DDP, FTP, and FSTP, and other strategies, but we just have one GPU. And this is fairly important as well, this bfloat 16 mix, because especially notebooks, for some reason, totally mix, so 16 mix, seem to lead to instabilities. For this demo, I just let it run for one epoch. And then there are some other things with checkpoint callback. So you see that the checkpoint that we saved has this format, and this was for the hour bar. Okay. So this is also the tensor board that where you can see your loss and so on. So if you train for longer, it might be interesting to see. At this moment, it was empty because it's the first time that we're using it.
Paolo?
Yeah.
Sorry, there is a question.
Yeah.
Could you show again how to get to that code? It was from GitHub.
So are we speaking of someone with access to Red Hat?
Red Hat, yes.
OpenShift. Okay. So if people are here, which I assume is where you land, I'm not entirely sure, then we go on data science projects. This person should put in the GitHub handle here. Mine is Paolo Fraccaro. And they should have, if they registered, one workshop session for them. So they click on it, workbenches, and they kick it off, or either is already going, and then open here. I would suggest just to engage with either Romeo or Blair, Benedict, just for people that have this problem. It should be fairly straightforward, especially if you are enabled here. Otherwise, this is where we would find these on TerraTorch. Should I keep going?
I believe yes. So the recommendation is to write again in Slack if people have other questions or want to deepen more into this topic. Thank you.
Also because on Slack, you'll be able even to share screen and so on, which is something that we cannot do here, right? But hopefully it is a little bit clearer after having shown again. So,
thank you.
Yeah, I haven't really spent time here, but what happened is just the model has done one epoch. It took about 4 minutes and so on, did the validation. What I wanted to show before, so we have this information here, blue, green, red, NIR arrow, and so on. If there was something different here, we basically would have a mix and match. So imagine there would be just blue, green, red. So we would have just 0, 1, 2. Or if the order would be different, then this would be different too. Is where we plug in the pre-trained weights in the right place. Okay, so we basically have a checkpoint hopefully saved in this location. And this is a little utility function to run the test set and to print some of the results. So as I was saying, this is kind of the simpler example that we're going to look at today. And we see how another thing that is kind of important as well that I didn't say is this one, right? For this checkpoint that I trained, the backbone has not been trained. So it's frozen. And the only thing that was trained, and we can see it, yes, is the parameters of the decoder, that would be. So we can see that even without modifying, because we're looking at HLS data and the model has, knows about HLS data, already on this data set, we got a 0.63 IOU on burn scars. The reason why also we can do that is also because the task is very visual, and also the the multispectral aspect can be leveraged. But we can see that, for example, with just one epoch, frozen backbone, for these places where there is very heavy contrast, it's almost perfect, right? For these other ones where there is less contrast, or rather there is contrast but just on very specific areas, it has an intuition that something is going on there, right? What I did was to train, let it train for 100 epochs, so still frozen. So we haven't changed the encoder. And we can see that with 100 epochs, we haven't changed the encoder. How, for this case, things started really being a little bit better. And this is kind of important to mention because the point of doing this pre-training, if possible, is really just combining it to a decoder in a way that the embeddings that come out from the encoder are already relevant, so you don't have to change it. However, in some use cases, or if you want to really squeeze the last inch out of your application, your results, then you basically can put here false, and then here you would have basically, instead of 20 million parameters, you would have the whole 324 parameters that are trained. So we can see that after under epoch frozen, we go from 0.67 or whatever it was, 63 to 0.62. We have a little bit more definition on these, contrast-heavy examples. Here we start actually having accurate predictions. In this one, still there is work to do, right? But 0.82 on this data set, is already quite interesting. So we run this example through through this notebook, which I guess also when you're learning is ideal, because you can have all these functions to plot and so on. The other thing, and that's the way that mostly me and my colleagues use TerraTorch, also because this can be used in actual jobs and so on, so you can just launch it and forget about it, is these configs. So I'm going to, if people want to do the same, I'm going to shut down my kernel. And now here I should get no kernel. I initialize the kernel again. And this is just for the sake of showing you that we can kick off the same thing, this one, and I'll show you this in a second, should be exactly the same, also through CLI. So we can run it like this, should start, kick off. The printout is fairly similar to what we saw before, and we could do the same like this, right? We could basically do TerraTorch, fit, and so on. This is gonna run, and what I wanted to show you is the actual, and I'm going to do this one, but possibly I will not do the other ones as well. But hopefully you start seeing some similarities, okay? So if we do, for example, like this, I'll do this. Yeah. So we have, in this config, we have a data part. And the data part basically is the data module. You see that we are looking at the same exact data module. We have the same attributes. This one actually we provided in the config, but is not even needed, because as it says here, we use all 6 bands of the data, so we don't actually need to do any of this, but is something that is going to come up also in the AGB one. But you see, is exactly the same, and basically it goes all under in a YAML file, these init args for this class. So it's almost if we are doing this, right? We are basically using this class, and we are providing all this for the class to be initialized. Then we have the same here. So we have a checkpoint callback that is being set up on the trainer, right? Accelerate. So basically, we're doing the same, but we're doing that in a config file. And in the end, the model. Prithvi-EO, pre-trained is true by default, so it is actually not is here. Image size, and this is something that I didn't mention because these data sets don't have this information, but Prithvi-TNL has basically the possibility of using these time and location embeddings, and if they are provided through the data set, then you should basically use either time only or time and location or location only. So yeah, we basically have exactly the same with the optimizer and so on. Now, if we close this one, we go back here. Possibly this has finished. Yeah, has finished. For some reason, when you do it in here, when it runs the validation, it has this awful printout, but there you go. It completed. So this is the first use case. We take Prithvi, and this is Prithvi, but as I said, in TerraTorch, there are other models that can be leveraged too. And fairly easily, fairly quickly, we got to something useful for this use case. I'll shut down the kernel again. This is important because there is just one GPU, and if you still have the kernel running on one of the notebooks while you start the other one, you won't be able to do very much. I'll close this one, and then I'll go through the other use case. So in terms of being difficult, this is more difficult than the previous one, and I think is less difficult than the next one. Again, all the requirements are fine. Download, but actually here we're just unpacking things. This one should be a little bit quicker. So this is a random subset of the data set that is here somewhere. Yeah, there you go. This one, which is actually a little bit bigger, but for the sake of this, we just made it a little bit smaller. In this case, we have different folders for training and validation. We have a similar format. These are data sets that NASA created originally. They follow the same convention. And possibly I'll go a little bit quicker in some areas, but not this one, right? So in this case, because this data set is multi-temporal, and the data requires also a little bit of specific operations that we do under the hood. This is a specific data set that we're using, so it's not the generic one that we're using, but it's something that is basically imported from TerraTorch data modules. We see the usual things, right? So the batch size, number of workers. This one wants the data root, and then it knows once the data root is given that there are these two folders, that there are the splits and so on. The important thing to mention here is this one. So in train transforms, if you remember before, we just had the D4 and the 2 tensor. Because this is a multi-temporal data set, and the data is loaded up in a particular way, we need this operation that prepares the data in a way that argumentation likes, digest, so we can apply our transformations, treating each individual timestamps individually. And then we can, after the transformations are complete, we can basically put it back how it's supposed to be to go to Prithvi for a multi-temporal task. So you'll see in a second, but there are 3 timestamps. So this operation of unflattening again requires how many timestamps we actually need. The data module itself, because it's this specific one on this data set, has already the mean, standard deviations. This version is much smaller. I think the bigger one is actually 3,000 chips or something like that. These are the categories that we are going to try to segment. So natural vegetation, forest, corn, soybeans, wetlands, developed, so that would be urban stuff, open water, winter wheat, alfalfa, and a number of others, plus other. And to make it visual, this is how it looks like. So we have 3 timestamps at 3 different time points, 3 different seasons. And this is the labels that are specific to the US. So this data set is specific to the US. And let me be precise. It should, yeah, the USDA crop data layer is these labels. Okay, so you can see that for patches, relatively big patches, these labels seem, reasonably good, especially for some things. This is clearly a river, for example. But then there is this spottiness. So for sure, this doesn't help the model. It's not like the burn scar before, where you had all these edges very well defined and so on. But for example, for this one, you see how is quite smooth. Then we have about 450 training, 250 validation, and 250 test. We go back to our definition of the model and definition of our trainer. And this is fairly similar to what we had before. The difference that we have here is just that the number of frames is 3 frames. And the number of classes is 13 classes. So you can see that just changing a few things with basically the same exact architecture. We plug in this case, the TNL version, for example. We basically, with the same architecture, so a backbone, Prithvi, some necks that allow us to put the data in the way the UNAT decoder wants. So we select the right indices from the transformer blocks. We reshape it to image, and in this case, we also give the effective time dimension to preserve that. To take that into account when we do the reshaping. And we then apply the learned interpolation to pyramidal to allow then the UNAT to do its job. again, we here have all the weight loading on the patch embedding. This one, if you run it somewhere else that is not the cloud, possibly this will be a little bit more more helpful, because you'll be able, for example, to kick it off even through the command line, and then you can go back and look at all your logs. That you know, if you look at, I've just run burn scars so far. So here would be the checkpoints, and here there are two because I ran before the one through the notebook and the one later that I show you through the other one through the CLI. So we didn't look at it before, but we can look at it now. So there is some sanity checking that is going on to make sure that the model is happy with the data that is fed. Then again, we went just for one epoch, frozen backbone, and this takes just maybe a minute or so. Here again, you basically see that the parameters now are a little bit more, but still the backbone that we are training is frozen. So this we won't be able to train. Obviously, if you think about the user experience while you do this, even a few minutes seem an eternity when you just stare at something that like this that progresses. So that's why possibly the CLI is maybe a little bit better, because you can basically just kick it off if you have a job, or if you have you know, some terminal that is just running, and then you can still load up your checkpoint and run, for example, just a test set, or maybe just run your visualizations to be able to interpret the results or also visually. This should take really maybe 30 more seconds. While it does that, are we doing all fine? Anything that not clear, or we're doing well? Okay, I'll take it as all doing well.
Yes, it's fine. No question. Oh, let
Okay.
me check. All good.
All good. Perfect, Maria. Thanks. Thanks. So that's really good to see. We try to have examples that really are easy to follow and can show some different things of both the model and the library. So it's just running through the validation set. In this case, is taking a little bit less. And if I'm not mistaken, this one is actually 224 by 224. The images are. So it takes a little bit less to run. We should have a checkpoint saved. Again, our utility function that is slightly different than the previous one, because we're not leveraging the general general data module. We're leveraging this specific one. And we can see that with this best checkpoint path, we have the model. Okay, so this is a glitch, and hopefully I can just pick it up where I was. Let's see. It's starting it up again.
Meanwhile,
yeah.
Paolo, I have a question for you.
Sure.
So Victoria Sarmiento, it looks that the model is able to differentiate between different types of crops, which is fantastic. That
Okay.
is usually very difficult with machine learning algorithms. Could you talk more about that, like the types of classes that have been tested?
Okay, so let me just check one thing. So I just want to make sure that we can just pick it up from where I was, which hopefully is the case. So I think I have to define, maybe because I can talk over it basically through when I plot the results, hopefully. So this should be that. And the only thing that I think I don't have to run is the training, although it takes just a couple of minutes if I had to. Let's see. Okay, this is loading. Let's see. So yes, this is promising. Yeah. So we'll see in this screenshot. In this plotting and in the scores that with one epoch it is kind of really hard, right? We're looking at 13 different classes to learn, and again we have frozen the encoder, right? So it is a lot to ask. When I do instead the other one that has been trained for 100 epochs. By the way, I didn't say, but you see here 68, 69. I let it run for 100, but the best checkpoint was around 70-ish for all of them. So you see here that for the Jakarta index, which is the IOU, a different way of calling IOU, mean IOU, is about 15%, which is not great, right? And we'll see how this looks different to what we have done before for the burn scar. In a second, we should see the plot, and I'll also kick off the next one while we go over the plot as well.
And while we are waiting, there is also another question then. Can you specify as many time periods beyond 3?
So, okay, first question, while that runs. Okay, let's do this last question. Last question is, you can specify almost as many as you want, with the caveat of the model has been pre-trained with the, so this 3 actually comes from the Prithvi-1, because this data set was released with Prithvi-1, Prithvi-2, and also Prithvi-1, but can adapt to different number of timestamps. Prithvi-2 was pre-trained with 4 timestamps, and we also heavily shout out to Benedict on the call that worked on that, but we heavily worked on data prep and identifying long enough time series for us to cover up to 1.5 years. And but you can have different length of time series, right? Ulic, which is one of the other collaborators on this Prithvi-2 project. So we pre-trained the model on Ulic with heavy involvement from them. They have a use case that you'll see if you look in the technical report, that where they use the up to 10 timestamps for land cover classification and crop classification as well. So that's flexible. Okay, so even with one epoch, there seems to be, obviously, this is not good, right? But there seems to be some classes, for example, in this case, this is water, that are kind of picked up, right? And some redness is picked up as well, but is a speculation to say that the model has learned much. Okay. So if we look at the pre-train is a loaded word in this in this context, the fine-tuned model that I let run for about 100 epochs, so from 66, we can see already that the MIUU went up almost threefold, right? 2 and a bit, and we can see how this is reflected in the predictions. So I would say that it seems to pick up some classes, and this is, I'm not an expert in the use case. It seems to pick up some classes better than others. I would say there is a lot of so the green one often seems to be right. But there is also some over prediction. Let's say, for example, this one, right? This one is I won't say it's perfect, but it is actually, you know, quite meaningful. Not having really optimized the model itself, I think there is still quite a lot that can be squeezed from the model on the full data set. For context, on Prithvi-2, I think we got about 0.50 MIUU, so there is still about 0.15 to go. And even there, you know, I think we could have done more to push it. The thing is that for MIUU or you know, even accuracy per se in this one, if there are some classes that are fairly similar, then you predict one or the other out of 13. There are so many possibilities that the model can be wrong. So generally on 13 classes of things that are very similar, many of them, I think is not too bad. It's not too bad. So another thing that one could do is maybe specialize the model on just one crop and predict just that one crop, and maybe have some another loaded word mixture of expert thing that where each model is specialized on just one class. I hope this somehow replied to the question. So yeah, same here. If we wanted, there is this multi-temporal crop config that is basically the specular to what we have done here. I'm not gonna do it, but if you guys want to have a try, please do so. I'm going to shut this down again, so we can start with the last use case. So we started from the first one where, you know, we had just one binary or just one interesting class to predict, binary segmentation. Did pretty good on that one. Here we can see that the model was able, at least for some classes, to learn quite easily again. And this is a more involved and more difficult task. And then we go to the last one, where it is going to be quite challenging for the model to learn, and you'll see in a second why. And we are doing this anyway. I'll show also the results of something similar that we have shown. We have done in an IBM, but we do this because this is a regression task. Okay. So the task itself is above ground biomass prediction. Is you know, very important to monitor vegetation and related use cases. So here again, the first cell is just unpacking the data. This is a data set that was on a specific type of forest or ecosystem that biome that is called taiga. And in this case, we're using the generic non-geo pixel-wise regression data module. So this is another one of those generic data modules that we created to make it fairly easy for people just to come in with their data. The models are there. You plug this in, and you're good to go. For this one, if you remember, the Bernska one had all the data in the same place. This one has actually dedicated folders for each of the trained data, the validation data, the test data, and so on. Because the data is already in different folders, the regular expression that we use to pick up the data is just, start.tif, because the data is already in the different folders that we're interested in. There is no need of split files or anything like that. Because it's not the dedicated data module as we had before, we need to provide the means and standard deviations. This is the 0 to 10,000 range that we see in a lot of HLS tiles in those tiles, and also Sentinel. So that's why maybe it's not between 0 and 1, or people are familiar with computer vision with between 0 and 255 and so on. This is the thing that we were talking about before, right? So the data, these files, have all the 10 bands that HLS provides, and we're just interested in the 6 Prithvi was pre-trained on. So this is the syntax that we're interested in, and we are basically putting some placeholders for TerraTorch to understand that this has 10 bands. We are giving the proper name just for the ones we're interested in, and then we're saying, oh, to this data module, we're saying, by the way, I'm just interested in these ones. And then the data module will just do it by itself. Again, no data replace equal to 0, and no label replace equal to -1. So we have about 1,600 training samples and about 400 validation. So the reason why I'm saying that for this data set is fairly difficult to learn, especially without unfreezing, especially with this little data, is the following. The labels for this above ground biomass estimation come from this JEDI data set that is basically a sensor that passes and measures points. And therefore we don't have those beautiful labels that we saw before for burn scars or even for multi-crop. We just have these points. And my colleagues basically created the patches around these points. And when we train, what happens is that we are going to predict the label on the full picture, on the full area, but the loss is just calculated on these points that are available. Hence, we have actually down an ignore index equal to -1, because when is no data, so there is no point, we have -1, and with the loss we can basically disregard those points. So you can imagine how much information is actually in terms of quantity, in terms of pixels that we had for a similar size data set that has full labels against something like this, right? Right. So we're good to go to the modeling piece, and I'll, if you give me a second, I'll just kick this off. I'll kick off also the training itself, so we can go back as we did before and chat about the differences for this use case again as well. Okay, so this is starting. We go back here. We still have the usual suspects around the checkpoint. Nothing really changes here on the trainer. You can see that with the same structure, you can adapt to different data sets quite easily. But let's look at the model itself. So as we said, we build our models around this task. And this task, we have a classification task, a segmentation task that you have seen before. And for regression, which is what we want to do, because we basically, these numbers or these points have a value that goes between 0 and 400. So we have a pixel-wise regression task, which means image in, image out, with image out being a regression, pixel-wise regression. We can still reuse the encoder-decoder factory, and it's fairly similar, right? So we have the backbone again, and we use Prithvi-300. We want it pre-trained. Number of frames this time is just one timestamp, and usually just I guess out of curiosity, because we're looking at things that do not change a lot in time. These might be monthly composite or even season composite or something like that. So the important thing for this application is that we don't have clouds. Therefore, we're happy doing some pre-processing and stacking everything together. Again, the backbone bands that we need to load up the patch embeddings. And then same as before. So we kept using the UNAT decoder. If you look at the examples, in TerraTorch, maybe we can go there if we have time. There is another fairly popular one that is called the UPNet decoder, and that is fairly similar. You would have different decoder arguments that you give to it, but in the end, the preparation here would be fairly similar. This time, rather than the cross-entropy loss that we use for the other semantic segmentation task, is a root mean squared error. And in terms of the loss, that's the only thing that we want to do. Here, I change the learning rate because of previous experiments that I had done. It seemed to work a little bit better or go down a little bit faster. So this should be complete. We can load up. Again, this looks more similar to the first one because we're leveraging this pixel-wise regression task, and data module is a little bit quicker, and you can see that generally the model has struggled a bit with learning with just one epoch and that little amount of data with frozen backbone as well. So the test loss or the test RMSE is not generally awful because for this application, okay, there are models that might go beyond this, and for sure. but generally is not super bad in the order of magnitude. The problem is that the model hasn't really learned, and you see, for example, on this patch that we really had a few, right? And here it didn't really learn much. This other one that I pre-trained has improved a little bit, and I stressed a little bit in respect to this first model that we trained together. However, there is still a long way to go, and I'm going to show you, I guess, what a good model would do in a second. So the point of doing this use case anyway is to give the instruments, the tools for people to get started and being able to use the regression task for their own applications, or even this AGB one, and push it until the limit. So we see that we went down a little bit in terms of RMSE. For this one, we don't really see a massive improvement. Well, I guess this one looks more something that is a little bit more about picking up features on the ground, and sometimes also these plots are a little bit misleading because of the contrast that we might have on a single patch. Then things look a little bit darker. Here we can see that we start, spotting some features around, at least. There are still some artifacts. What we see here, at least, this is there is no forest, for example. There is not a lot of vegetation. Then we can see that it started understanding where it has to predict low values generally. Okay, so this is good to see. But as I said, it is still a long way to go. Again, we have our config file, and is the specula of the notebook, and we can see that we use the generic non-geopixel-wise regression data module, and the pixel-wise regression task. So if we go, and I've got the zoom bar here that is in the middle, I'll move it, not sure if you see it. If we think about this use case and people are interested, as IBM, we have fine-tuned a different version of Prithvi, and I'm showing this for the sake of showing you, the art of the possible to some extent, and is on Hugging Face as well. So it's called the Granite geospatial Biomass. And there is a collab notebook that you can look at, and you can basically see how the predictions. If I start from the top here, it just explains what it's going to do, and the 0 shot for a single biome, a few shot for a single biome is what the data that we use for this application. But without going through this one, which is not really the point here, is just showing you how, with much more data and much more curation, then you can actually start having or looking at something that makes sense, right? So you have the predicted AGB. This is 0 to 200. And you can see that where the forest is more dense, you have higher values, and the opposite where is bare land as well. Same here, and on this big forest as well, right? And here what they're doing is this globally trained model that they have specialized on AGB. that they have fine-tuned, then they try to specialize it on this specific biome, which is the taiga one, taiga boreal forest. It's a pity that these other cells are not pre-filled for us, but it just shows that then we can fine-tune with a much lower loss to this specific biome. So this is everything that we wanted to show today. I hope it was interesting, easy enough to follow. Hope I haven't seen any technical issues except the one of my own, but it was just a second to go back to it. And the point was really to give you some overview on the model, the capabilities, but also about the library and how one could be leveraging that for their own applications. As I said, Romo, who is on the line, is leading the TerraTorch development with the global team. And it would be really happy to see more people using it, engaging with it, asking for features, submitting their own data sets, PRs, everything that can, everything that is in TorchGeo, we can access because we're kind of compatible by default. We build on the top of TorchGeo and Lightning. So if a data module or data set is PR'd in TorchGeo, then we would be able to consume it. And the difference really for us is more focusing on the modeling aspects and making this composability of models. So if we go on TerraTorch itself, TerraTorch itself, we have a list of models that we have available, and more than that we keep adding, right? The GeoBench results show that on average, Prithvi-2 is the best model. However, for some maybe more high-res task or some specific task, others might be better. So the point is really democratizing and making accessible this technology in terms of foundation models to everyone. And the way that you would basically, if I go to the examples, use even other models is fairly similar, right? So this is DOFA, another model that people might be familiar with. In terms of the modeling itself, is again the encoder-decoder factory. Now the order is a little bit different, but different decoder. The backbone, you just call it, and then you can see, for example, the reshaped token and so on. So I'll just tell people to play with it, get involved. These for the people that had access, this workbench should be available to you for the next day or so. So if you want to do more experiments or bring in maybe even your own data, now that you have an example of how to use both the general or generic segmentation and regression data module, then it would be the perfect occasion to do that. Any question, Maria, and anything? Are still people there? Okay.
I don't see question, but
Yes.
I want to ask you a very general one for everyone, specifically for the less technological people here.
Yeah.
I want that you specify which are the minimum capacity of the computer they need to use for repeating this experiment. So not now, but in the next days, if they want to repeat it again, what they need to have. So
despite we are freezing the backbone and therefore there are less parameters, a GPU is, I guess, still needed to do the fine tuning. We are using the less performant GPUs that are the same that people can find on Colab for free. So if people want to, they can just let's see if I go here, it should be still this branch. No, it's not this branch. I'll show it again. Examples. There you go. So people should go here on download these notebooks on Colab, and everything should be working because the GPU that we are using is the same. On your own laptop, if you have one of the latest Macs or anything like that, you might be able to do it even on your own laptop. Those laptops, latest laptops that have GPUs, you would be able to do that.
Okay, so is it possible to repeat what you showed us, also simply having a good computer, let us say in this way, and using Colab?
Using Colab for sure. The defined good computer, meaning the one that can run the GPU like the latest Macs for sure. We actually. Lara was telling me that he has experimented on fine tuning on one of these laptops. The safe bet is Colab because it's free and the data is not huge, so you should be able to do it.
Excellent. Then I have another curiosity. I'm checking now. There are no other questions. So 300 million, 600 million. There are these two versions.
Yeah.
Which is the best one to choose, advantages, disadvantages? If I have to decide what of them I can use, and what I have to consider.
Yeah, so maybe I'll go here. Or maybe I can actually go here. So this is the technical report, right? So one thing to consider is the environment that you have available. So the 600 million model is bigger on the GPU. So there might be some GPUs that may struggle with it, despite, especially for some tasks. Despite we were able to run it on V100 just fine, which are the older GPUs. Going beyond that, I think it depends what you want to do. Meaning, if we look at that graph that I showed you before, right? This is the overall performance and on the Geobench data set or framework, where these are the individual data sets performance, okay? So if we go here, generally the scaling law seems to be respected on average, which means that if you pick a bigger model, and you can see, I'm talking for our models because for other models, we don't have the comparison between smaller, bigger. But if you just look at the blue ones, 100 worse than, that, by the way, will be open sourced also, the 100 million at some point. I still don't have a timeline, but we'll do that. So 100 worse than 300 and 300 worse than 600. So if you go for accuracy, then the 600, and you have the specs, then the 600 generally better. However, the 600 also comes with a higher tendency of basically overfitting, which in some data sets might come out. And for Geobench, it was fine, but it's something to bear in mind, because especially if you have little data, that has more chances of kind of really overfit on that little data. here I just wanted to show out of curiosity what I mean for better on average. We have our models on the right here, with the 600 being always the one on the extreme right, far right. And you can see that generally is the 600 million is better than the 300 million, but for some use cases, for example, for this one, it is. For this one over here, actually the 300 million is on par, and for this one, it seems like this 300 million is even slightly better of one of the versions of the 600 million, right? So these are repeated experiments 10 times, so there is some variability, but do you see what I mean? It depends on the application. On average, you can see that the one on the far right is always better than the one on the purple one, but it depends. So once we open source also the 100 million, then what I would do really is experiment, develop with the 100 million to even look if it makes sense to some extent, have a use case around that, because you see that especially the new 100 million one, most of the time gives you already some generally good outputs, not on par with these ones, but it's not terrible and it's much lighter. Okay, but then you can commit either to the 300 or 600, depending on the specs and use case. Possibly I didn't give you a straight answer, but I don't think there is a straight answer.
Yeah, no, it's clear. It's clear. And then I believe that it's very important also what you underlined, that adding more parameters, you have to pay strong attention to the overfitting.
Exactly.
So it's not even true that the more, the better. The more, it depends.
The more doing in the right way, generally the better, I would say.
Yeah,
but
paying attention on the overfitting,
exactly,
obviously, as it is also in statistics, as a matter of fact. It's nothing new. It's exactly the same, exactly the same. And then I have a very last question for you, which again is very general, probably is also difficult to answer.
Okay.
If we compare these large language model, geospatial large language model, with the normal large language model, obviously the second one, the latter, are much more advanced and they can be used by everyone. So think about ChatGPT, everyone is using ChatGPT. When, in your opinion, also our foundation model, geospatial, will be available in the same way? First of all, in your opinion, it will become true sooner or later? And can you give a number, like in 1 year, in 5 years, in few months?
So can I say it depends? So
yeah, but you have to say also it depends on what.
Exactly. I'll argument that. So we're working on that line of research as well. There is a paper that is on preprint that I think Dial at Dial paper. There you go. So if people want to have a look, so it depends, because the gap that we're trying to fill in terms of accuracy, as far as I can see now, is still a little bit wide on the specific task. Okay, so if you took, for the vast majority, if you took something like Prithvi or any other of these specialized vision models, and you asked to perform the task basically that you're interested in, that is only based on the visual information, the gap is still quite wide. So if you go for performance, then we're not quite there yet. The VLMs, the geospatial VLMs like Earth.io, I think the game there is trying to fill this gap. We're not there yet, as far as I can see, because we're asking a lot of an LLM to interpret tokens that come from a VLM for some things that are very heavily, visual and different to what the models have been trained for. So I'm optimistic that maybe combining different decoders with the VLM, some SAM-like or some Dino-like, we'll be able to get closer and closer. The thing that I see more likely is that we go more towards, and I was hinting at this before, an agentic way of running things, where for some things, VLMs can be fine even for geospatial, but then for the more spatialized things, we have different skills that are represented by the different fine-tuned models, and people will be able to interact with it in a ChatGPT, like, if we want to use that term, through text, but actually is not a model that is doing the operations. There is a model that is orchestrating a number of other models that have different skills. And that I think in the next few years, not very far, at least on a basic level, we'll be able to see as well.
And this is it's a very good answer, Paolo. Also because I know that there are many young people attending this webinar, and so it's good for these young people to know that there is to do also.
Yeah.
And so it's not it's a field that it's growing, and there is interest behind that. And so yeah. Young people, challenge yourself in this field, which is not easy. And so I'm very happy to know people like Paolo, who is so good in this field, but there is a lot to do also for other people.
Absolutely. And then, we're in a really cool field because it can really have an impact on people, on communities, but there are these big organizations like NASA, ESA, that really have an interest in providing all this data. So there are so many different aspects. There is the more technical aspect, there is the more application aspect, there is, it is really differentiated as a field. So there is a little bit of everything for everyone, depending on your interest.
Excellent. Thank you so much. And in thanking you, I will call back also Andrea. Andrea, ciao. Did you like the?
Yeah, I like very much.
I hope he says yes.
Yeah, of course. Was very, very much of interest.
And yes, I want to thank you again, Paolo. See you also next week. And now I leave the floor to Andrea for the closing.
Yeah, just one thing, I wanted to give a shout out to my colleagues also in the background that helped us running the session. So thanks, Blair, Romeo, and Benedict. And thanks for the opportunity.
Thank you. Ciao, ciao.
Ciao, ciao.
Thank you very much for this excellent webinar. I also want to thank Benedict, Romeo, and Blair, who assisted the participants during the workshop. We also want to thank AWS through the AI for Good Impact initiative, who has provided the computer resource for this workshop. And of course, thank to Maria for having moderating the event. I want to mention that the workshop material will be available from the neural network. And of course, you can also watch the recording on YouTube and the neural network as well. I want to remind you the next planned event for the GUI discovery will be another workshop organized by NASA and IBM on geospatial foundation model, will be on March 26th on foundation models for weather and climate. I'm also pleased to inform you that we are organizing an in-person workshop at the For Good Summit on July 9th on the innovating geospatial solutions for the SDGs, the role of GUI and foundational model in shaping a sustainable future. So stay tuned for those exciting development in GUI and geospatial foundational model. And I thank you all again for your participation. And with this, let me give back the floor to Anna. Thank you very much.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.